is all about nuclear change. Specifically, we're going to look at fission and fusion, but it's going to be split into two parts. The first part is going to focus on the bigger picture and how nuclear change fits into our existing understanding of chemistry. And the second part is going to zoom in on the details and the mechanism of fission and fusion, and then some of the implications those things have for society and technology. So you can watch one or both of these lectures. They can be paired together really well, or you can also watch either or, depending on what you need. So, looking at the big picture, one thing that I think is hard when you're studying chemistry is that there's just so many details you need to keep track of. And sometimes when we are zoomed in on the details, we can forget the big picture. And that just makes it harder, in my opinion. So, what we're going to do right now is take time to really zoom out and look at the big picture of how nuclear change fits into our understanding of chemistry, so that it kind of has like a good place to live in your brain and it's connected to other things instead of just being this like lost cloud of details. So, we want to start our big picture journey by zooming all the way back out to our basic introductory fundamental definition of chemistry, which is the study of matter and how it changes. So remember that matter is stuff. Stuff is made of atoms. We have atoms of all the different elements on the periodic table. Those atoms are made of subatomic particles, your protons, your neutrons, your electrons. So the study of matter and how it changes begs the question, well, how does it change? So there are three main categories to think about when you think about matter changing. You've got your physical change, your chemical change, and your nuclear change. So our lecture today is focusing on nuclear change, which is why it's circled, but the other ones are part of how we understand this larger idea of matter changing. So, a physical change is when the atoms are staying the same element and they are also still the same compound. They are not rearranging themselves. So, I think the easiest example when you're thinking about physical change is to think about water. And you know that when you put water in a freezer, it is ice, room temperature is liquid, and when you heat it, you have gas. In all of those phases, it's still a water molecule, right? You have your hydrogen and your oxygen, H2O, and that doesn't change. So the hydrogens never change, the oxygens don't turn into another element, and the compound doesn't change. Your atoms don't rearrange themselves. You have water molecules through each phase. What does change is their energy and how they physically move around each other. And those things are how you get physical changes between atoms, right? The atoms don't change themselves and they do not rearrange. So that's your physical change. Next, we have chemical change, and chemical change is what most people think of when they think of chemistry. It's when your atoms are the same element, but they are now rearranging to form different combinations of those atoms. So this is just an example of a combustion reaction, like if you're burning this fuel. So you have CH4 and then you have oxygen. and they go through this chemical change. That's what the arrow represents, right? And on the other side, the atoms themselves have not changed. You still have the same atoms, but they have rearranged themselves to form different compounds. You have different combinations of atoms now. So now the oxygens that were together, you now have two of them with a carbon, and you have hydrogens with oxygen now. So that's your chemical changes. Again, this is what kind of the most, our brains go here first when we think of chemistry for most people. And then our third one is nuclear change. And for nuclear change, the atoms actually are changing elements. So you have an atom of one element goes through a nuclear change, and it turns into an atom of a different element. So kind of adding some stuff to our basic chart. We have a general understanding of what's going on with our atoms and our particles in each one. But that still leaves the question of like, why, right? Like, why do these different changes occur? And there's kind of two things to think about. I'm highlighting isotopes here because we're focused on nuclear change. And isotopes, we don't think about a whole lot when we're talking about physical change and chemical change. And that's because most of the time, our isotopes that are going to be involved in physical changes and chemical changes are stable. Right? An isotope is when you have an atom of the same element with different numbers of neutrons. And we know that there is always an isotope that is more abundant than the other ones, and usually like dramatically more abundant. And those are the ones that are stable, right? The ones that are most abundant are the stable isotopes, and they are the ones that are doing these chemical changes and physical changes for the most part. So we don't talk about isotopes a whole lot when we're focused on physical change and chemical change because it's just assumed that it's the stable versions. The word isotope comes up a lot when we talk about nuclear change, and that's because it's the unstable isotopes that are involved in nuclear changes. That is kind of like the underlying mechanism of how a nuclear change can happen, which we'll go into more on the next slide. So this line here is just, again, to help your brain kind of understand, like, this is why we talk about isotopes with nuclear change and why we don't really talk about it with the other ones. Physical change and chemical change, isotopes are stable. Nuclear change, isotopes are unstable. So just finishing up our nuclear change here, the reason why the unstable isotopes matter is because it all has to do with the strong nuclear force, which, remember, our strong nuclear force is what holds the nucleus of the atom together. And that is determined by the ratio of the number of protons to the number of neutrons within the nucleus. That ratio ultimately determines whether or not the atom is going to be stable or not. So nuclear changes are very much focused on protons and neutrons and what is happening in the nucleus of an atom. When you're looking, I'm just going to go backwards here. When you're looking at chemical changes, the star of the show is the electron. You're still talking about stability when things are going through chemical changes, but it's not the stability of the nucleus, it's the stability of the valence electrons and what the valence electrons are doing. So electrons are the key player when we're talking about chemical changes. And then lastly, over here, when we're looking at physical changes, subatomic particles are not they're not the thing that's like driving the physical change. What's driving physical change is mostly about your thermal energy, heat, and what sort of changes are going on with heat and also sometimes pressure. So you know from your life that like water will be liquid at a room temperature. What that means is that the water particles can kind of move around each other and slide around. When you stick water in the freezer, it becomes ice. And just looking at it, you know there's not a lot of motion occurring there. So what that really means is when you put something in the freezer, heat is being removed. And when you remove heat, the molecules slow down. And when they slow down, you get a phase change. You get an ice for water, um, a piece of ice. On the flip side, when you heat water, like on the stove, you are allowing those particles to move a lot faster. So they are gaining kinetic energy from the heat and they move around a lot faster. And that's what we call gas and what we see as gas. So changes to the physical state is a lot about heat, sometimes pressure. And then in general, it just has to do with like the relative motion and maybe the position of particles, right? Like, because you could chop a piece of wood and you're not changing heat so much, but you are a little bit, and ultimately you're just moving the particles away from each other to get that physical change. Okay, so here's our broad, again, look at just thinking about, well, matter. Chemistry is all about the study of matter and how it changes. What are the different types of change? How can we define those changes by looking at what's going on with the atoms and the particles? And then ultimately, what determines what type of change it's going to be, which is looking at here the physical changes about heat, chemical change. It's all about stability of your valence electrons and the activity of what's going on with them. And then our nuclear changes has all about what's going on in the nucleus with your protons and your neutrons and your strong nuclear force. So since this is a lecture on nuclear change, we are now going to start zooming in further to nuclear change and looking at the strong nuclear force and what's going on with that. So we're going to say goodbye to physical and chemical change for now, but hopefully you have nuclear change hanging out with them in your brain. Okay, so moving in, zooming in a little bit on nuclear change. So previously, we talked about how atoms of one element change into atoms of a different element. The process through which that happens, there's a few: fission, fusion, or radioactive decay. So again, this lecture is focusing on fission, fusion. Radioactive decay will be a later one. So these processes release huge amounts of energy. And the reason that they release so much energy is because of the changes that are occurring to the ratio of the protons and the neutrons in the nucleus. So we know that in the nucleus, you've got your protons and your neutrons. We know that protons are positively charged and therefore they're going to repel each other. But the nucleus is not flying apart, and the reason for that is because of the strong nuclear force that you have between the neutrons and the protons. And there's that really strong attraction. So it's a strong nuclear force. There's a lot of energy binding those particles together. And so if something happens to overcome that force, huge amounts of energy get released. Basically, you have to have like the perfect Goldilocks ratio of protons to neutrons for the strong nuclear force to hold everything together. And a simple change to the ratio can upset that force, and then the whole thing the bond will break and it will all come apart, and in the process release a crazy amount of energy. So that energy release is what we associate with fission and fusion for the most part.